9.7 Lesson 3, Taylor Polynomials and Approximations. The objective for today's lesson is you'll use Taylor's theorem to determine the maximum error in approximating a function at x by its nth degree Taylor polynomial centered at c, evaluated at x. So we have some vocabulary, and we are going to be learning about Taylor's theorem, and we'll see what this means, Lagrange form of the remainder. But before we can get to that, we need to discuss these four vocabulary terms prior to Taylor's theorem. So we have some function f. For example, f of x could be e to the x, or f of x could be sine x, or cosine x, or natural log of x. So we have some function f. And we would like to evaluate the function f at a particular x value. And the value of the function at x is called the exact value. Now, yesterday and the day before, we learned about nth degree Taylor polynomial approximations for f centered at c. So we can approximate a function with an nth degree Taylor polynomial centered at c. So we can approximate the value of the function at a particular x value by evaluating our nth degree Taylor polynomial centered at c for our function f at the same x value. So this is called an approximate value, because we're evaluating our nth degree Taylor polynomial centered at c that approximates the function f at that x value. There is a difference between the exact value and the approximate value, and that difference is called the remainder. So the remainder is r sub n of x, and it is the difference between the exact value and the approximate value given by our nth degree Taylor polynomial centered at c that approximates the function f. Another way we can express the same relationship that we just talked about, again, this is the remainder. We could also write f of x, the exact value, is equal to the approximate value plus the remainder. This is just another way of expressing what we have here and here. What do we mean by the error? It is the absolute value of the remainder. So when we talk about error, we're talking about the absolute value of the remainder. So we can take our remainder and put the absolute value around it, and that would give us what we call the error. Without the absolute value, the remainder could be positive or negative, depending on if the approximate value is less than the exact value or greater than the exact value. But when we put absolute value on the remainder, we say we're talking about the error. So what is Taylor's theorem? So we're looking at Taylor's theorem here. It states if a function f is differentiable through order n plus 1 in an interval I containing c, which is the center of the nth degree Taylor polynomial approximation for f. If a function f is differentiable through order n plus 1 in an interval containing c, then for each x in the interval, there exists some value z between x and the center of the polynomial approximation, such that the exact value of the function at x is equal to, what is this? This is our nth degree polynomial approximation centered at c for the function f. In other words, this is our approximate value plus the remainder. This is our remainder. I want to emphasize once again that the part here that I'm circling in gold now, what is this? It's the nth degree Taylor polynomial centered at C that approximates our function f, as we learned yesterday and the day before from this definition of nth Taylor polynomial centered at C. So that's exactly what that is. So here you have an nth degree Taylor polynomial centered at C that approximates our function f. So if you evaluate the nth degree Taylor polynomial at x, you'll get an approximate value for the function evaluated at x. And the difference between the exact value and the approximate value is called the remainder. So Taylor's theorem tells us that the remainder, which I have braced here in blue, is given by the n+1th derivative of the function evaluated at z. And what is z? It is a value between the center of our polynomial approximation for f and the x value at which we're evaluating the function f. So z is some number between the center of our polynomial approximation and the x value at which we're evaluating the function f. So according to Taylor's theorem, the difference between the exact value and the approximate value, called the remainder, is equal to the n+1th derivative of the function f evaluated at z, as I just explained what z is, divided by n+1 factorial times x minus c to the n+1 power. So that's what Taylor's theorem is. And this remainder that's given in Taylor's theorem, that is called the Lagrange form of the remainder. So going back to vocabulary, the remainder is the difference between the exact value of the function evaluated at x and the approximate value for the function evaluated at x. If you put absolute value, then we say we have the error. So this is what we mean by the error of our approximation, where p sub n of x is approximating the function f evaluated at x. So what we want to do is we want to use the Lagrange form of the remainder to have an idea of how close our approximation is to the exact value of the function evaluated at x. In other words, we want to know if we can put an upper bound on this error. What is the largest this error could be in a particular problem? Taylor's theorem tells us the difference between the exact value and the approximate value, called the remainder. But if you look at the remainder that's given here, which is of course called the Lagrange form of the remainder, there is one issue. And the issue is, it states that the remainder r sub n of x is equal to the n+1th derivative of the function f evaluated at z over n+1 factorial times x minus c to the n+1 power. The problem with that is we don't know what z is. We just know that it's somewhere between the center of our nth degree Taylor polynomial approximation for f and the x value that we're trying to the x value at which we're evaluating the function f. So z could be somewhere between x and c. So even though Taylor's theorem states that the remainder is equal to this quantity, we don't know exactly what the remainder is because z is given as a value between x and c, and we don't know exactly what z is. So this is Taylor's theorem. It tells us the remainder, but because z is not z is between x and c. So it could range anywhere between whatever c is and the x value at which we're evaluating the function. And for that reason, we don't know what the exact remainder is. We just have a possible range of values for the remainder depending on what we choose for z, z being between c and x. So we have this theorem and it tells us what the remainder is, but we can't really use it unless we're able to have some idea of how large this remainder could be. So what we're going to do is we're going to consider an upper bound for this error. And when I say error, of course, we have to put absolute value on the remainder. So let's take a look at that. So we're going to put absolute value on the remainder. So now we're talking about the error. And when you put absolute value on this remainder, look at what we have here for the Lagrange form of the remainder from Taylor's theorem. You can see that we have n plus 1 factorial, and that's going to be positive. So we don't really need to worry about that when we put absolute value on the remainder to get the error. But what we do need to concern ourselves with is the other parts of the remainder, which could be negative. So for example, x minus c could be positive or negative depending on if x is greater than c or if x is less than c. But when we put absolute value on the remainder, we want to make sure we have a positive quantity. So we put absolute value of x minus c to the n plus 1 power. And then also, the n plus 1th derivative of f evaluated at z could be positive or negative in the remainder. So if we put absolute value on the remainder to have the error, we want to make sure that that's going to be a positive quantity. So we put absolute value here. So that's how we go from the remainder to the error. But more significantly, we want to know how good our approximation is. In other words, what's the most we could be off by? How much could we be off from the exact value? What's the greatest amount that our approximate value could be off from the exact value? So we want to put an upper bound on the error. So here's how we put an upper bound on the error. We just say, looking at the remainder from Taylor's theorem, and first of all, let me go ahead and get rid of this part here that says max. I'll get rid of it temporarily. So if I get rid of that max part, then really what I have here is an equal sign, meaning that I took my remainder from Taylor's theorem and I put absolute value around it to give me the error. Because what is error? The error is the absolute value of the remainder. So as simple as that, all we did was we took the n plus 1th derivative of f evaluated at z and put absolute value around it, and we took x minus c to the n plus 1 power and put absolute value around it. So when we do that, we go from remainder to error. But we still have the problem that I mentioned a minute ago, which is that we don't really know what the exact remainder is because we don't have an exact value for z. All we know is that this z is somewhere between the center of our polynomial approximation for f and the x value at which we are evaluating the function f. So we don't have an exact value for z, so we don't know the exact remainder. What we want to do is we want to think about how large this remainder could possibly be, we want to put an upper bound on this remainder. And how do we do that? Here's how we do it. We're going to basically say, look at this remainder. We have n plus 1 factorial, which is going to be a fixed value when you choose a particular value for n. N just tells you the degree of the polynomial approximation centered at C for the function f. So n tells you the degree of your Taylor polynomial approximation for f centered at C. So once you have an nth degree Taylor polynomial, the n plus 1 factorial quantity will be fixed. And then you are evaluating the function f at a particular x value. So once that x value is chosen, then the quantity x minus c would also be fixed for the chosen x value and the center c for the nth degree Taylor polynomial approximation for f. The only quantity that has z is this quantity here. And because z is coming from a range, this quantity that I am now circling in black, it could vary. It could have a range of values. So we're going to think about how we can put an upper bound on the error. Basically, we're going to say, make this the largest it could be. And if you make that quantity, which can vary in a particular range, the largest it could be, then what you're doing is putting an upper bound on the error. So now we look at our first concrete example, and these are the instructions. Use Taylor's theorem to obtain an upper bound, which is what we just talked about, an upper bound for the error of the approximation. So we have our function f of x is equal to e to the x. It is approximated by a fifth degree Taylor polynomial centered at 0. And the problem is this. We want to approximate f of x is equal to e to the x evaluated at x is equal to negative 0.1. Approximate the function f evaluated at negative 1 at negative 0.1 by evaluating the fifth degree Taylor polynomial centered at 0 at x is equal to negative 0.1. So when we do that, this is what we have. This is the exact value, and it is equal to the approximate value plus the remainder. So the remainder is the difference between the exact value and the approximate value. And when we put absolute value, we have the error. So what we want to do in this problem is to put an upper bound on this error. And as we saw from Taylor's theorem, here's what we know. Taylor's theorem tells us that the remainder is equal to what I'm circling in red here. So r sub 5 of negative 0.1, that's the x value, x is equal to negative 0.1, is equal to the sixth derivative of f evaluated at z, where z is between x and c. So c is the center of our Taylor polynomial approximation, which is 0, and x is negative 0.1. So z is somewhere between negative 0.1 and 0. So we have the sixth derivative of f evaluated at z divided by 6 factorial times negative 0.1, which is x, minus c to the n plus 1 power, and of course n is 5, so this is to the 5 plus 1 power. This is the remainder according to Taylor's theorem. What we want to do is we want to consider the error, which is the absolute value of the remainder, and we want to put an upper bound on the error. And as discussed, if you want to consider the error, you put absolute value on the remainder. And then if you want to put an upper bound on the error so that you know the maximum amount that your approximation could be off from the exact value by, that is the purpose of putting an upper bound on the error. Here's how we're going to do it. As discussed earlier in the lesson, we're just going to put absolute value on the quantities that could be negative so that they're going to be guaranteed to be positive. And to put an upper bound, we're going to look at the quantity that could vary depending on what z is and say, let's make it the biggest it could be so that the error would be bounded so that it could be no bigger than that. So we're going to use that now to put an upper bound on the error. So when we do that, this is what we have. The error is going to have an upper bound, and this is going to be the upper bound for the error. So we have n plus 1 factorial. 5 plus 1 is 6, so we have 6 factorial. And then the absolute value of x minus c to the n plus 1 power. So we have x is negative 0.1 and c is 0. So the absolute value of negative 0.1 to the 6th power. And most significantly, we're going to say, let's make this quantity the biggest it could be on this range for z, so that we put an upper bound on the error. And this would tell us the most that our approximate value could be off from the exact value of f evaluated at negative 0.1. So in this problem, our function f was e to the x. So if you take derivatives of this function, you will always get e to the x. So the first derivative will be e to the x. The second derivative will be e to the x. The third derivative will be e to the x. The fourth derivative will be e to the x. The fifth derivative will be e to the x. And the sixth derivative would also be e to the x. Our original function is f of x is equal to e to the x. So I may replace the sixth derivative of f evaluated at z by e to the x evaluated at z. Now we need to consider the function e to the x. Let's look at the graph of the function e to the x. The graph of e to the x looks like what I just sketched here in gold. And here is, of course, x is equal to 0, and here I have something like x is equal to maybe negative 1. And you can see that e to the x is an increasing function. So for z values from this interval, e to the z will be maximum at the right endpoint of the interval, at z is equal to 0. So if I want to choose the z value from this interval, for which e to the z will be maximized, I would choose z to be equal to 0. So e to the 0 is 1. So I can now replace this here with 1. So what that tells me is that the error can be no bigger than this quantity, the absolute value of negative 0.1, which is, of course, 0.1. Raise that to the 6th power and divide by 6 factorial and multiply by 1. So this is the most my approximation could be off from the exact value by. This quantity is approximately 0.000000000139. In other words, that's the maximum amount that my approximation for e to the negative 0.1 could be off from the exact value of e to the negative 0.1. In other words, it's really good. To help you understand the idea visually, I have gone ahead and graphed the function y is equal to e to the x, which is in red, and I have gone ahead and graphed the fifth degree Taylor polynomial centered at 0 that approximates f of x is equal to e to the x. And you can see that the graphs are virtually indistinguishable for values of x that are close to the center of the approximation. And of course, we're approximating e to the negative 0.1 by evaluating this fifth degree Taylor polynomial centered at 0 at negative 0.1. And if you look at the graph, at that value of x, which is negative 0.1, which is about here, the two graphs are indistinguishable for the window settings that we have. And our work with Taylor's theorem puts a numerical value to the accuracy of our approximation, telling us that our approximate value for e to the negative 0.1 using the fifth degree Taylor polynomial centered at 0 that approximates e to the x can be off from the exact value by an amount no greater than this. And this is a very small amount. So we can be confident in the accuracy of our approximation to 9 digits after the decimal, or we'll say 8 digits after the decimal. 1, 2, 3, 4, 5, 6, 7, 8. So we have accuracy to 8 digits after the decimal in our approximation. So we'll look at a second example, same idea. Use Taylor's theorem to obtain an upper bound for the error of the approximation. The function that we have in the second example is f of x is equal to sine of x. It is approximated by a third degree Taylor polynomial centered at 0. So f of x is approximated by our third degree Taylor polynomial centered at 0. And we want to approximate f of 0.1. In other words, sine of 0.1 by evaluating our third degree Taylor polynomial at 0.1. And we will use Taylor's theorem to obtain an upper bound for the error of the approximation so that we will know the most our approximation could be off from the exact value by. Let's look at what we're trying to do visually. So in red, we have the graph of the function f of x is equal to sine of x. And in blue, we have the graph of the third degree Taylor polynomial centered at 0 that approximates sine of x. And you can see that for values of x that are near the center, the two graphs from our window settings seem indistinguishable. They become more distinguishable as you go further away from 0. So we would expect that our third degree Taylor polynomial used to approximate our function f at x is equal to 0.1, which is close to 0, would be a pretty good approximation. And if I were to point out where 0.1 is on the graph, it would be right here. And you can see from the window settings that we have that the two graphs are visually indistinguishable for this set of window settings. We want to use Taylor's theorem to put a numerical value on how good our approximation is by putting an upper bound on the error so that we can be confident that our approximation can be off from the exact value by an amount no greater than that. So as we've seen earlier in the lesson, we have Taylor's theorem, which gives us the Lagrange form of the remainder. And when we put absolute value on the remainder, we say we have the error. And as we've discussed, we can put an upper bound on the error by making that one part from the Lagrange form of the remainder that can vary because of z coming from the range between x and c. So make that the biggest it could be, and you have an upper bound for the error. In our problem, c is equal to 0 because our Taylor polynomial is centered at 0, and x is equal to 0.1 because that is the x value at which we want to evaluate the function f, approximate that value by evaluating our third degree Taylor polynomial at the x value of 0.1. So now, according to this result that we have, which is from Taylor's theorem, this is what we need to find. So we need to find an upper bound for the error, we have to find the maximum that the fourth derivative of f could be for a range of values from this interval. So our function is f of x, and here's the first derivative of f of x, here's the second derivative of it, here's the third derivative of it, and here's the fourth derivative of it. So the fourth derivative of our function is, in fact, sine of x. So what we really need to consider is what should go here for the maximum value of the fourth derivative of our function evaluated at z, where z is between 0 and 0.1. Now go back to what our fourth derivative is. As we just saw, the fourth derivative of our function is sine of x. So we want to evaluate the fourth derivative at a z value from this interval at which the fourth derivative will be a maximum. So go back to the derivative, go back to the graph of the sine function. The sine function is the derivative, the fourth derivative of sine. And sine of 0 is 0, and sine of pi over 2 is 1. So the graph of the sine function looks something like this. So here is 0, and this is at pi over 2. Pi over 2 is about 1.57. So you can see that on the interval from 0 to 0.1, the sine function is increasing. So the fourth derivative will be at a maximum value for z is equal to 0.1. But there's only one issue with that. We're trying to approximate our original function f of x is equal to sine x at 0.1. So that's what we're trying to approximate to begin with. So although by theory the maximum value of the fourth derivative evaluated at z, where z is between 0 and 0.1, will occur at 0.1, we can't really use that because we're assuming that we don't have a calculator and we're trying to approximate sine of 0.1 to begin with. So what do? And this is like the question that a student had asked earlier. Asking about, well, is it proper to put an equal sign here and here when z is between x and c? And my response was, the idea here is we're just trying to put an upper bound on what the error can be. So it's okay to do that. And in fact, in this particular problem, we can even go beyond this interval because, again, all we're trying to do is to put an upper bound on what the error could be. So we want to choose a z value, even if it's outside of this interval, at which we can easily evaluate the sine function. So there are certain special angles at which we can easily evaluate the sine function. For example, first of all, the sine function for any x will range between -1 and +1. So if you wanted to save time, you can just put a 1 here because the fourth derivative of sine can be no bigger than 1 for any value of z. If you wanted to fine-tune it a little bit, you could, because we know that sine of pi over 6 is equal to 1/2. And pi over 6 is, pi is about 3.14, so pi over 6 is more than 0.5. So pi over 6 is outside of this interval for z. So we have z is between 0 and 0.1, and we know that 0.1 is going to be less than pi over 6. So if we evaluate the fourth derivative at pi over 6, for sure it will be greater than the fourth derivative evaluated at a z value from this interval. So we're being super safe. This is like the error can be certainly no bigger than that. So this is putting an upper bound. And we like to use that because it's the a value, it's like the smallest known value that we can be confident in for the sine of z, where z is in this from this interval. It's actually, we're using z outside of this interval, but that's okay. We're just saying this is, we're confident that sine of z will be no smaller than this, or will be no bigger than this. So sine of z will be no bigger than this. That's basically what we're saying. Let me correct myself from what I had said earlier. Sine of z will be no bigger than this. So for sure, because sine of z will be no bigger than this, the error has to be smaller than this particular value here. So we're putting an upper bound on the error. So what that means is that we can be absolutely confident that when we're approximating sine of 0.1 using the third degree Taylor polynomial centered at 0 that approximates the sine function, our approximation for sine of 0.1 by evaluating our third degree Taylor polynomial at 0.1 will have an error that's no greater than this amount. In other words, we are absolutely confident that our approximation is accurate to at least 5 digits after the decimal, because our work shows that this is the upper bound for the error. And of course, we actually went beyond the theoretical upper bound by finding a practical value at which we can put an upper bound to this quantity by choosing to evaluate the sine function at pi over 6, which is outside of this interval, but it's safely outside of it, so that we can be absolutely confident that the maximum value here has to be even less than 1/2. So for sure, this is an upper bound for the error of approximating sine x by p sub 3 of x at x is equal to 0.1. Today we used Taylor's theorem to determine the maximum error in approximating a function at x by its nth degree Taylor polynomial approximation evaluated at x.